Ramanujan for G is now available on the Google Play Store. Try it out for free.
Good morning, students. So today we are going to start this new chapter, fresh chapter, electrochemistry. So as its name suggests, this word is made up of two different words, electro plus chemistry. Electro means it means something related to electron or electricity, and chemistry, we know chemistry is a process of bond breaking and bond forming. So how this electron or properties of electric properties of certain substance associated with the chemistry or chemical changes, this is what we are going to study in electrochemistry. And whenever we are talking about the electrons, so what we have seen earlier, whatever we have studied, that from where there we will get certain information. And what we have studied, where we have seen the flow of electrons from one chemical substance to the other chemical substance. We have studied it in the redox chemistry or redox chemistry chapter. So means the redox process, electrochemistry will basically deal with the chemistry of the redox processes, and whatever the information that we have got uh, from the redox chemistry, we will be using that information for the good of people. And that branch of chemistry where we will do that is called the electrochemistry. So electrochemistry deals with studying electrical properties of electrolyte solutions, and electrolyte solutions we have studied earlier in ionic solutions, ionic equilibrium as well. So electrical properties of electrolyte solutions, so one way, or the interrelation of the chemical transformation and electrical energy, or the electrical transform chemical transformation and electrical energy. Means in redox chemistry, if you look at certain processes are spontaneous processes, they can occur, they have potential to occur naturally. And if they are spontaneous, we have read in thermodynamics, spontaneous processes are those processes for which free energy is negative, means delta G, or that change is negative. So that process is a spontaneous process, and means some energy is released which is free to do certain work. And that is how the magnitude we get in the negative form. So whatever the value of that energy is which is released during the chemical transformation, the idea is, can we use that energy for our use of for our different purposes. And this is what people tried to do, and they made different devices. The batteries that you know is one of the such device. We can convert chemical energies, and the energy that is released during a spontaneous chemical transformations to produce electricity, and that electricity we use for running many devices like our mobile, our laptop, many things that we use. But currently all the sort of batteries, they are actually electrochemical devices, and they convert spontaneous chemical transformations into the electrical energy. Now the thing is how this chemical transformation which has happened, and the spontaneous chemical transformation and the energy released is converted into the electricity, because these chemical transformations that we have focusing mostly on in this chapter electrochemistry are the redox processes, as I said. And a redox process, actually redox means reduction plus oxidation. And oxidation, what happens, the electrons are released or electrons are lost during the oxidation. And now that electrons, if the oxidation and reduction both happens in the same vessel, so that electron will go to some other substance, and there it will combine and it will reduce that substance, and so the reduction will be happening there. So the oxidation and reduction usually happens together, and if there are substances, they are mixed together, so it will happen. Only oxidation or only reduction cannot happen, because electrons cannot have a free existence. Their independent existence, they always found to be combined with the particles. They can be produced for a certain time, but they cannot exist independently. So these electrons, if whether in the oxidation, if this electron is released, there must be someone to accept it. Or if there is a, if and the reduction, if there is no free electron, as I said, reduction cannot happen. So the thing is, if the two vessels in a vessel, if you have the mixture of substances, one of that can give electrons and another can accept, so this reaction, this process will happen, and this is what we call the redox process or redox reactions. But now the idea here is if you separate out these two processes, the oxidation and redox processes at two different places, you make them happen at two different places. And now allow this electron, whatever electron that has been produced, as I said, electron can be formed, they can be produced, but they will travel and immediately they need someone to accept them because they cannot have independent existence because of very a small size and the charge is there and the very tiny particle that easily combine to anything. So what happens, so suppose I am just separating out these redox reactions that was happening initially in the same vessel that we have studied in redox chemistry. Now I am separating them out, and at one vessel oxidation is happening. If I allow oxidation to happen in another vessel, I can allow reduction to happen. But if I put these two substances separate, that this thing will not happen altogether because there is no one to accept electrons at from the where the oxidation was happening, and there is no source of electrons at the reduction half. So what once I connect them together through an electrical wire or by anything which can conduct electricity or which can allow the movement of electrons, then this reaction will start happening at oxidation. What in the oxidation vessel, the oxidation will happen and the electrons will produce, and those electrons will travel through a wire to go to the another place, and there these electrons will be used for the reduction. And while we know if I am allowing electrons to move through a circuit, through a wire or something, some conductor, it means the electron is flowing in a certain direction. And if I put something there, I can sense the electricity being produced. And that is how the electrochemical cells are being made. And similarly, opposite to this, as I said, the electrons are there. Is the another source of electrons is the electricity. If you can produce electricity, electricity is there because of the difference in the potential. And how the because of the difference in potential to make the potential equal, what happens? The electrons flow from one part to the another part, and so one can use electricity as the source of electron, the free electron, and there one can make certain chemical reactions also happen, and that chemical reactions which are not happening altogether by its own because this was a not a spontaneous process. Delta G was positive for this. Now the electrons, if I provide electrons to there, so electrons, they, as I said, they cannot have independent existence. They will go combine with the substance or the material there. Now it changes its property after combining electrons combined to a certain material. The property of substance, the property of that substance changes completely. It was not, it is not to the previous, the property is not to the same whatever was previously. So what will happen? So now it will react, it will make certain other substances, and this is what we use in electrolytic processes. So we use electricity to break certain chemical compound into different substances, different compounds, or different elements, or we can use chemical to chemical substances, and when they will react, will form something else, and then during this process, this redox process, this is a spontaneous process. Electrons are allowed to travel through a definite circuit, and so we can produce electricity. So this is what we call the interrelation of chemical transformation of electrical energy. So we use chemical transformation to produce electricity, and this chemical transformation that produces energy is the spontaneous chemical redox reaction. Spontaneous means delta G negative, and redox means reduction and oxidation is happening there. And then we can use also the electricity to make non-spontaneous reactions happen. That is what the opposite is, the interrelation of chemical transformation of electrical energy. If you look at the use of this electrochemical processes, and if you remember the electron transport chain that happens inside our body, particularly if I don't remember much, those who know the biology they can understand it. It happens inside the cell, particularly in mitochondria, somewhere in the mitochondria, and that is how the energy is produced, and that we use for our survival and of different purposes, the different functions work we do. And that is how that energy, the electron transport chain, is nothing but a redox process, and the most of the energy that is produced in the cell due to the oxidation of glucose is because of the electron transport chain. And the Krebs cycle, those things you see, it's there all the redox processes mostly, and this because of this redox processes we are getting energy. Not only we, all the living forms are getting energy. So that is what we study in the electrochemistry. That is also part of the electrochemistry. A large number of metals, sodium hydroxide, chlorine, fluorine, and many other chemicals are produced by electrochemical methods. Particularly, that we will see when we will see the group chemistry separately. So sodium metals, how the metals are extracted, like sodium metal. How will I get sodium metal? Pure sodium metal, something like this kind of process that we do, and also the purification of certain metals. This is how we get the metals, certain metals, alkali group metals we get by electrochemistry, method of electrochemistry. Some metals, though we can extract, but we don't get the purified form. To purify them, we use electrolytic processes or electrorefining processes, and that is what the certain metals that are purified using this electrochemical processes. Aluminium, copper, zinc, we purify them. So electropurification we use, like the knowledge of electrochemistry and the knowledge of redox reactions, and with the knowledge of redox reactions, the idea, the application of those redox reactions that we study in electrochemistry, and that one of the application is the purification of certain metals. Batteries and fuel cells convert chemical energy into electrical energy, and that is what batteries I have said. The fuel cells, now we are looking for an option alternative for the diesels or the gasolines or the fossil fuels. And there now we are looking, we are seeing at the fuel cells, and that fuel cells, what do? They are also cells. They convert chemical energy into electrical energy, and that means they are also part of the electrochemistry. We study them in the electrochemistry chapter, and we know how useful they are in various instruments and devices. Without them, it's very difficult to survive. Your, as I said, the mobile phones, how you can see how important it is for you now. The laptops and many other substances that they are running on this, and even that now electrical vehicles are also coming. So electrical vehicles, they also use batteries or the fuel cells. The reactions carried out electrochemically can be energy efficient and less polluting. And so what we, if you burn fossil fuels, what we will produce? Mostly the carbon dioxide, NOx, SOx gases, that is what we produce. But what if we do electrochemistry, we don't produce any gas. A certain chemical change is happening, it is going from one form to another form. This is all what we do. And though while discarding batteries, once they are totally exploited, that may produce certain energy, but that may cause pollution. But the thing is, in that way, we are creating less pollution to the environment, and particularly that to the air pollution will be minimized using these electrochemical devices. The transmission, if you look at the body, as I said, the energy production, electron transport chain, those things is the electrochemical processes. If you look at other processes like the impulses at the of miss the movement or the transportation of whatever the pulse, the information that we get. Suppose I pinch you at certain place, immediately you get signal that someone has pinched you. It means that immediately whatever this information that a signal goes, these are particularly the forms in the, it starts in the form of electrical signal. It goes to synapses, and synapses means, the sensory cells are there, and the nerve cells are there. Those two nerve cells, they join together, and they're joining while they are called synapse. And while at that processes, this electrical signal has actually passed into one nerve cell. It goes and it ends where the nerve cell is ending. So it gets converted, this electrical signal, into the chemical signal, and there with certain chemical compounds are there. They do react certain reactions, and they go enter, and by doing that they enter another sensory cell, and this is how this happens at the synaptic vesicles, where two nerve cells join together. And thus now they are after going inside that another nerve cells, what they again do certain chemical transformation, and now this chemical energy or the chemical is now converted into the electrical impulse, and then it goes to our brain, and then we sense. And you can see how within a second, a fraction of second, everything happens, how fast it happens. And they are all electrochemical processes. So the transmission of sensory signals through cells to brain and vice versa, and communication between the cells are known to have electrochemical origin. So even if you look at the electrochemical cell, like the we have inside our stomach, and we get certain acid reflux, and that acid, because of the electrical electrochemical signals, that acid reflux happens. We have ion channels, and those ion channels, they also work on the electrochemical principles. So different ion channels, without ion channels, it is very difficult for, it is impossible for our possible to us to survive. So what this actually ion channels, they also work on the laws that we are going to study here. So if you study this particular chapter, you understand it, so somehow you are also going to get certain information how our body works, or different parts of our body works. And so electrochemistry is therefore a vast interdisciplinary subject. As I said, it has importance in biology, it has importance in the engineering, and this kind of the devices that we are making is part of engineering, the chemistry that we know. So in this unit, we will cover some of its important elementary aspects, as it's only the elementary aspects there in your syllabus, so only few elementary aspects or conceptual things we will be studying in this chapter. We shall specifically study the production of electricity from energy released during spontaneous chemical reactions, and energy released during spontaneous chemical reactions. That kind of cell we call the galvanic cell. We will study what is a galvanic cell and the use of electrical energy to bring about non-spontaneous chemical transformations, and that is what it happens inside an electrolytic cell. So spontaneous chemical reactions we do and will produce energy, that is the part of galvanic cell, and it happens inside the galvanic cell. The electrical energy, use of electrical energy to make non-spontaneous chemical transformations happen, is is the part of the electrolytic cell, or that we study in the electrolytic cell. So it means the electrolytic cells provides energy, electrical energy, to make certain non-spontaneous reactions happen. I mean, anyway, so let us, since we are studying about the electricity, all the times we are producing electricity or using electricity, so let us understand how the electricity actually uh, transmit from one place to another place, or that we know the certain things, the non-conductors and conductors, these concepts that we know already, just as I just mention them. So those substances which do not allow electric current to pass through them are called non-conductors. Non-conductors are also called insulators. And the example I don't think I need to give, but anyway, the wood, plastic, glass, rubber, the air at normal atmospheric pressure, they are all insulators. The conductors, they are substances which allow electric current to flow through them. And the example of the conductors are, we know, all the metals, usually the salt solutions, molten electrolytes or molten ionic compounds, and the molten metals, they are all conductors. Graphite, as I mentioned, the salt solutions are also conductors. So conductors can be divided into two groups, and the metals and electrolytes. And metals contains metals, all the metals, and graphite. And the salt solution, we know salt solution is the electrolyte. So metallic conductors, if you look at the metallic conductors, are they conduct electricity or electric current by movement of electrons without undergoing any chemical change during the process. So in the metals, what happens? We see what happens. That we see the movement of free electrons from one place to other place, and so the electric current is conducted. What we don't see inside the metals, that what we also see, that the atomic nuclei do not change their position. They are fixed at whatever the place they are in the metallic lattice or metallic crystal, and then and only the move what moves is the electrons, free electrons, and the metals nuclei are fixed at their positions in the metallic crystals. So they conduct electricity. Metallic conductors conduct electricity in both solid as well as molten state. Examples are all metals and graphite. Graphite is also called the metallic conductor, though it is not a metal, but it is considered as a metallic conductor because the way it pass electric current is similar. The mechanism is similar that to that of the metallic conductor. So graphite is considered as a metallic conductor. And for graphite, I have explained it earlier. Um, it has certain dangling bonds, from those dangling electrons actually move through the one layer, and the particular layer, and so the electricity is being produced. And that layer is what the conjugated pi electron system. And that because of that conjugation, they move very fast, and so the graphite conducts electricity. And however, electrolytes are a bit different than the metallic conductors. So in electrolytes, what we see the movement of ions. So electrolytes are what? They are actually composed of cations and anions. And if their solution is the aqueous solution that we take, so we get there certain cations and certain anions. So electron that was produced from the by an element which became cation after relieving its electron. So that electron goes to some other substance and make it anionic. So we see existence of cation and anions. And now they are in the solution form, and we know in the solutions particles can move. So now this, if you create certain potential difference, so these cations and anions moves in certain direction, and since they can move in certain directions because of the potential difference, so they conduct electricity because of the movement of cations and anions, or means the movement of ions. So the electrolytes conduct electricity by movement of ions in the solution. And the electrolytes can be of types, the strong electrolyte and weak electrolyte. If you remember, we have studied it in the ionic equilibrium. What is a strong electrolyte and what is a weak electrolyte? Let us again see what is a strong and weak electrolyte, because it might be important for you to understand here as well. So the compounds that completely dissociate into its ions when dissolved in water are called a strong electrolyte. So if suppose I add NaCl, and what we see, NaCl completely dissociates. So more than 95% dissociation is there. So more than 95% dissociation means if you add 1 gram or 10 gram of NaCl, so it will be 9.5 gram at least will be dissociated into Na plus and Cl minus ions. So NaCl is a strong electrolyte. So a strong electrolyte that almost may not be completely, but that almost completely dissociate into its ions, the constituent ions. Then such electrolytes are called strong electrolytes. And the example of strong electrolytes are all strong acids and all strong bases. And we know strong acids, what do? They immediately furnish H plus ions into the aqueous solution. If they furnish H plus ions into the aqueous solution, so they will also have anions. So all the strong acids are strong electrolytes. Strong bases also furnishes OH minus ions immediately into the solution, and they almost all the ions, all the molecules of the strong bases are involved in producing OH minus ions. So that is how we get the OH minus ions are there. So net charge is zero. So somewhere minus ion is produced, so somewhere plus ions will also be produced, like NaOH. NaOH dissociates into the aqueous solution to form OH minus and Na plus. And that we also know KOH is the similar thing. So they are strong electrolytes because they are strong bases. And there are some salts which also behaves as a strong electrolyte. As I said, NaCl, KCl, there are many salts that behave as a strong electrolyte. And what those salts are a strong electrolyte for which lattice energy is not very high and the hydration energy is sufficient to break these lattices. Because ionic compounds, what do they form lattice, and lattice because of the many ions comes in a most favorable direction, more favorable way, so that their energy is minimized, and the minimized to certain energy is released. That energy we call the lattice energy. And lattice energy actually is defined the energy that we provide to break 1 mole of the ionic compound, and in all those ions should go into the gaseous form. Whatever the energy that is required, we call the lattice energy. And that lattice energy, so we need to provide certain energy, and that energy, when ion is dissolved in water, what happens after ionization? These ions will be surrounded by water molecules, and this because of the water molecules surround them, certain interaction happens, and that interaction actually causes to decrease in the energy. Energy is released if any attractive interaction is happening. and so water molecules interact attractively to the different cations and anions, and so certain energy is released. That energy we call the hydration energy. So if hydration energy is more than the lattice energy, so usually we get this ionic compound is 100% ionized. If the hydration energy cannot overcompensate or compensate the lattice energy, or it's not nearby to the lattice energy, we see only few ions will only be dissolved or only be ionized. Only few molecules of non-ionic compound will be ionized, and so that ionic compound will behave as a weak electrolyte. So weak electrolytes are compounds that partially dissociate into its ions when dissolved in water. So this includes weak acids. We know weak acids only few H plus ions produces per molecule, and the weak bases, if only few OH minus ions we see. Not all the molecules of weak bases are involved in producing OH minus ions, and some salts. And what are those salts? As I said, if lattice energy is very high, and that cannot be compensated or overcompensated by the hydration energy, so that those ions, those salts will behave as a weak electrolyte. Now the coming to the electrochemical cell, as I said, the cell that converts chemical energy liberated during a redox reaction to electrical energy. So what is the chemical energy that is liberated during a redox reaction? That energy, this device, electrochemical cell, converts into the electrical energy, or the vice versa can also happen. So it provides electricity to convert certain reactions which were non-spontaneous, as we have seen earlier. That is why vice versa is known as electrochemical cell. So this is a device which can convert a chemical transformation. The spontaneous can use the energy of the spontaneous chemical transformation reaction. Whatever energy that was produced, it can convert into the electrical energy, or it can provide certain energy, electrical energy, to make non-spontaneous chemical transformations happen. So electrochemical cells can be of two types. One is called electrolytic cell, and another type is called galvanic or voltaic cell. So electrolytic cell is also a part of electrochemical cell, and the voltaic cell is also voltaic or galvanic cell is also part of the electrochemical cell. So let us look into the electrolytic cells as the electrolytic. So this is something, it is lysing certain things. So how it is made up of? Let us see its construction. So electrolytic cell, the one compartment is there. Inside one compartment, two metal electrodes are being put. They are dipped inside an electrolyte solution. This is the electrolyte solution. So electrolyte, what is electrolyte? We have studied. When electrolyte solution is there, already there in this compartment. Now two metal rods are dipped, and now if I connect these two metal rods with a battery, and this battery, whatever the battery, the positive end of the battery, it connects to whatever the electrode, that electrode we call in electrolytic cell anode, and the negative end is connected to the cathode. So what you see here, the anode is given the positive potential, positive end, and cathode is having negative potential in this case, also negative. And the anode, so what we see here, the electrochemical cell has mostly three components: what is anode, cathode, and electrolyte. Although there is some battery and a switch will be there to connect the battery, because you don't want this thing to happen continuously and this battery being discharged. So there must be certain switch, so that it will make this happen only when you want this to happen. So what happens? And anode oxidation happens. Always remember, whether it is the electrolytic cell or galvanic cell, at anode always oxidation will happen. However, the polarity, in the case of electrolytic cell, the anode is given positive polarity, but in the case of galvanic cell, anode is given negative polarity. How it is, that we will see later on when we will see galvanic cell. So an electrolytic cell is a device that uses electrical energy to facilitate a non-spontaneous redox reaction. So non-spontaneous redox reaction, that we know. So if a reaction is spontaneous in certain direction, in opposite direction it will be non-spontaneous. And as we know, because of the laws that we studied in the thermodynamics, so if a reaction is spontaneous in positive one direction, in opposite direction, reverse direction, it will be non-spontaneous. So for example, formation of water from H2 and O2 is a spontaneous process. So breaking of water to form hydrogen and oxygen is non-spontaneous process. And since formation of water from hydrogen and oxygen is spontaneous, that is why we see plenty of water on the earth. And hydrogen, we don't have enough hydrogen. And that is why even we do have quite high percentage of oxygen, but we don't have free hydrogen in that form, and that is how it goes. Whatever the source of hydrogen, usually living forms that use, they either use the mm, carbohydrates in the form of food, or they use water as a source of hydrogen. So what the formation of water is spontaneous, and the formation or the lysis of water to form hydrogen and oxygen gases are non-spontaneous process. So if you want to make that non-spontaneous happens, you cannot make that happen. Formation of hydrogen and oxygen means the lysis of water, you cannot make it happen so easily. You need certain things, some things to facilitate it, and that one example that we can consider is that we can use electrolytic cell, this device. So the electrolytic cells are the type of electrochemical cells that can be used for the electrolysis of the certain compounds. So it can be used as the electrolysis of certain compounds. For example, the water can be subjected to electrolysis to form gaseous oxygen and gaseous hydrogen. This is done by using the flow of electrons into the reaction environment to overcome the activation barrier. So this is how it happens. And again, so this is the electrolyte. Again, I am going to explain. So what oxidation will happening at the anode, and so this you can see here. This is a kind of shown in the anionic form. This anion gives its electron to form the neutral, the X plus E, and is the electron. So this electron loss happens at the anode. That is what we call oxidation is happening. And what we know, the oxidation is what, the loss of electrons, and reduction is what, gain of electrons. So the loss of electron is happening here. So the oxidation is happening at the anode, at this electrode, and the cathode, this electron is coming at the traveling through this, and it is coming to the cathode. So cathode is accepting electrons, so that the whatever that this cation of the electrolyte solution will come here at cathode. It will associate with the electron that is there, that has come to the cathode, and will form the neutral metal, usually the substance. So this is the from the electrolyte solution. X minus is the anion of the electrolyte. So X minus may come here, and that anion, and actually it is what we get, the anion is produced. So for example, in the case of water, as we saw, so the water, what happened in this, if you want to electrolyze water, so what the water, H plus ion will come here, and H plus one ion will accept electron to form hydrogen gas. And the OH minus ion, it will travel to this, because the positive polarity is given to the anode. So OH minus ion will move towards the positive polarity, and here what happens, it will form oxygen gas, and oxygen gas will be produced. And the oxygen gas, what the in OH minus oxygen, its oxidation number is -2, and if oxygen gas is formed, its oxidation number is 0. So the oxidation is happening here at the anode. So there are three basic components of an electrolyte solutions: cathode, which is negatively charged, and this is what we give the negative polarity. And what is was happening there, the reduction was happening at the cathode. And the anode, which was given a positive polarity of the battery that you see here, and so the anions are coming here, and what was happening, anions are losing their electrons. So what oxidation is happening at the anode, and anode is positively charged or given positive polarity. And then the electrolyte which provides the medium for the exchange of electrons between the cathode and anode. And that is how, so what happens here is, in the case of electrolytic cell, so that this electron is being used here. And if once this electron is being used, how this process will happen? So there must be somewhere the electrons to be produced, and so the anions are coming here from these places, all over the places, and producing electrons. So making this circuit complete. So that is how this is the role of electrolyte. When an electric current is passed into the circuit, the cathode becomes rich in electrons and develops a negative charge. That is what we know. So electric current is passed means we have switched on the battery, and we have switched on the battery as soon as what will this negative polarity is already there. So cathode will be flooded with the electrons, because electrons will be moving towards the cathode. So it will be flooded with the electrons, so it will become negatively charged, and the cathode becomes rich in electrons and develops a negative charge. So cations of electrolyte are now attracted towards the negatively charged cathode. This is what I have already explained. This results into the deposition of metals at cathode, or if it is a hydrogen that you want to produce, hydrogen will be there. So it also depends on the activity of the metal cation. If you use certain metal cation which is less active than the H plus ion of the water, so the hydrogen gas will be produced. And if the metal ion of that electrolyte is more active than the hydrogen, then what will happen? Then the metal will be deposited at the cathode. Simultaneously, anions of the electrolyte are attracted to the positively charged cathode and get oxidized. This is what we have just seen. Commonly used electrolytes in the electrolytic cells include water, and include water is very important for us. Because first of all, water provides medium, and without medium, that is how the aqueous solution that we are using means the ions, cations and anions are getting separated because of the water interaction with the water, and so that is why the water is important here. So commonly used electrolytes in electrochemical cells include water containing dissolved ions. Why water is used? To dissolve ions, to separate ions of the electrolyte. And with sodium chloride we also use sometimes. When NaCl is used as an electrolyte, sodium metals get deposited at the cathode and chlorine gas evolved at anode, and it is also used in production of oxygen and hydrogen gases from water. This is what we see. Let us look at the galvanic cell. So electrolytic cell, if required, we will see metal in metallurgy and more other processes. When we will study, we will see in a bit more details. Even in the S block chemistry, when we will study, we will see some flavor of the electrochemistry, particularly the electrolytic cells. And electrolytic cells to purify, to actually get metals, particularly S or S block metals. What we do, they are very active. So actually we use their molten salts, and then molten salts, because of the electrolysis, they get deposited at cathode, and that we take. Again, that we'll see later on. Let us look at the galvanic cells or voltaic cells. The, both are same name, galvanic or voltaic cells, and they are an electrochemical device, or they are electrochemical cells or devices that convert chemical energy of spontaneous redox reactions into the electrical energy. This I have explained much earlier. The example of the galvanic or voltaic cell is the Daniell cell. Daniell cell you might have seen earlier. So what is the Daniell cell? Then Daniell cell we use in the redox reaction, redox process. I have used the example of Daniell cell, if you remember. So zinc Zn and plus copper ion, so copper electrolyte. What do they do? The net reaction that happens in a Daniell cell is zinc solid and the copper 2 plus. When we use copper 2 plus in a copper sulfate electrolyte solution, what we get? Zinc replaces copper from the its electrolyte solution. This is what we are studying in the redox chemistry. So if zinc rod is dipped into the copper sulfate solutions, usually what will happen? Zinc will be dissolved, and it will form zinc 2 plus ion, and copper will be deposited. So copper solids will be formed. And this is what the redox reactions that we know from the redox chemistry, and that redox reaction is used in the Daniell cell to produce energy. So let us look at the construction of the Daniell cell. What we use, the two compartments are used, or they usually in any galvanic cells, so there are two different compartments that we use. One compartment cathode is dipped, and another compartment anode is dipped, and both compartments they can use the electrolyte solution. They can have the same electrolyte solution or with different electrolytes. So means the anion of the electrolytes can be same, or the anion of electrolyte may not be same. Anyway, the metal, the cation of electrolytes will be different in these two solutions. And so we have a anode and we have a cathode, and these two compartments, this part we call the anodic half, and this part we call the cathodic half. They are actually, the two behave as half cells. So this is we call the cathode half cells, and this is anode half cells on anodic half cell. And this cathode, in the case of galvanic cell, this anode contains zinc, and its electrolyte solution also contains zinc. So zinc sulfate, let us consider the zinc sulfate is inside this. And in the cathode, in the Daniel cell, which is an example of galvanic cell or the voltaic cell, in the cathode, the copper metal is used, copper electrode is used as a cathode, and in this the electrolyte solution would be the solution of copper 2 plus, and that might be the copper sulfate that we can use. And these two electrolyte solutions are joined together by a salt bridge. And what is the importance of salt bridge, that we'll see later. Very sorry. And in this case, if you remember, you can note, if you have noticed here, what you see, the negative polarity is given to the anode. In the electrolytic cell, what it was, a positive polarity, and here we see the cathode has positive polarity. So the polarity is reversed. However, the type of reactions will be the same. The anode also, whatever at anode, the oxidation will be happening, and the cathode reduction will be happening, same as it happens in the case of electrolytic cell. So what we see actually, that the electrical potential of this Daniel cell, when zinc concentration of zinc and copper ions is 1 molar, this is 1.1 volt. So the energy, the potential difference that it creates when the zinc ion concentration in this anodic half is 1 molar, and copper ion concentration in the cathodic half is also 1 molar. So what we see the electric potential is 1.1 volt, means the EMF of this cell is that we call electromotive force. What is that? We will see a little later. So you should just know the EMF or the electrical potential. The electrical potential is easy to understand. It is 1.1 volt. What does it mean? It means that if I add something to this battery, this cell, if I add some external device to it, and along which at which the potential difference at its two terminals of the device is less than 1.1 volt, if the external, this we call the external potential, if it is less than the 1.1 volt EMF, then what we will see, the direction electron will flow from anode to cathode, and so this cell will give certain electricity. And so this cell will give electricity, something like that. One can use this like a stabilizer, or the stabilizer also uses many other things like transformers or those things that you can see in the your physics class. So what we use, that if this is what we see, if you connect this to a bulb, the external potential is, if it's a bulb is zero, its external potential around its wire is zero. When they're there, if nothing is connected to it, so the electric potential, whatever the potential is less than 1.1 volt, so what we will see, the bulb will glow. And whatever, if the fan you connect to any device that you connect, so what we say that if the external potential that we, means the external potential of certain anything, any apparatus or device that you use, if it is less than the EMF of the cell or the electric potential of the cell, so what we will see, when E external is less than 1.1 volt, which is EMF of the cell, so the electrical potential of the cell. This is the example that we have taken for the Daniel cell, but this is true for all kind of voltaic or galvanic cells. So electrons will flow from the anode to cathode, and in this Daniel cell, the electrons will flow from zinc to copper. So zinc to copper, and then what will have, zinc will dissolve at anode and the copper will be deposited at cathode. So copper will be deposited here, so electrons will flow here, and electrons will come, and that electrons will be used here at the cathode, and the copper and electron will come here at this juncture, and this electron will combine with the Cu plus ion, whatever Cu plus plus ion is there, and the copper will be deposited here. And the zinc simultaneously, how this electron is being produced, from where that electron has come, because the zinc Zn plus is ionized, and we know that zinc is electrically more positive than the copper, and so its oxidation will happen. So zinc is oxidized, it produces electron, 2 electrons plus zinc 2 plus, and that is the electron that goes into the outer circuit to for the production of electricity. For production of electricity. So if an external opposite potential is applied, so this is what I'm saying. If the external opposite potential, this potential in the opposite direction to the potential that is here because of this cell. So the opposite direction, even though this is happening, this will happen. So an external opposite potential is applied in the galvanic cell, or and is even if it is increased slowly, the reaction continues to take place till the opposite voltage reaches the electric potential of the cell. So what we normally say, if there is no opposite external potential, what we see in this device is the zinc ion is actually dissolved. It produces zinc 2 plus and 2 electrons. Those electrons now travels through it and here, and if the electron is traveling to what we see, the electric current is produced in the opposite direction, in the opposite sense, and so electrons is coming to cathode, and that electron is coming here in the Daniell cell to copper, which is cathode, and that electron will be here and it will be now interacting at the surface with the copper 2 plus ion, and so it will be combined with the copper 2 plus ion to form copper solid, and of neutral copper, which is copper solid, and so the copper will be deposited here. It's called so anyway, so the copper will be here, and if suppose I use certain impure copper compound and I dissolve it using certain acid and I put that thing inside this, some impurities will also be there here. But what we see here, only copper will be deposited, not the other impurities. So that is that way. What can we do? We can purify copper. So what will be? Suppose copper with copper, some more impurity is also there, some amount. So that impurity will not be reduced here. Only copper will be reduced using this device. So that is how we use. And depending on the what kind of impurity it is, if that impurity is not more active than this, so it's redox depending on the redox potentials. So that we will see what is that potential. So and now opposite, the electron is moving and if the current is being produced, so if now we add opposite potential, and what we see how the current is flowing, because electron is moving from here to here and the electron is moving from here this direction, so this direction, because there is certain potential of this, so there is a positive potential, this is negative potential, and that is why electron is moving there, and how the positive and negative that we will see little later. So just remember these terms. And so if opposite external potential is connected, so we see, and if that potential is less than the EMF of the cell, the electric potential of the cell, we still see the flow of the electricity or the flow of the electron in this direction, or the electric current is flowing in the opposite direction, we will still see. But once this external opposite potential becomes equal to the EMF of the electric potential of the cell, what we see, there is no flow of electron, no flow of electricity in any direction. So when the external potential becomes equal to the electric potential of the cell, the reaction stops and no current flow through the cell. So when external potential, the is external is the device of whatever thing that you have added, if that has also 1.1 volt electric potential difference, and this cell has also 1 point, this EMF is what? It's the potential difference between two electrodes. So this is called the electric potential. So this electric potential and this electric potential is it's same. So there will be no flow of electron in any direction, no net flow of electrons. So there is no flow of electricity. And the example is I said zinc sulfate, copper sulfate is the electrolyte. And so what we see, if the opposite external potential is 1.1 volt, no flow of electrons or current, and no chemical reaction will be happening here. So there is no chemical reactions, no flow of electrons, nothing is happening. But once you keep the external opposite potential more than the EMF of the cell or the electric potential of the cell, so what will happen? So if external potential is more and this is in the opposite direction, so this is positive and this is negative. So usually you can see here, this is positive and this was negative. Now once you add the opposite external potential, so what will happen? So because of this, these wires are connected, so this cathode will become negative and sorry, this will become negative and this will become positive, and this will become negative and this will become positive, means what? So in this cell, electrochemical cell, so negative, what is negative is the anode. So cathode will become anode and anode will become cathode. So an node will behave like cathode and cathode will behave like anode. And so what will happen, the electron will flow in the opposite direction, and electron is flow in the will be flowing in the opposite direction. So current will be flowing also in this direction. Earlier, in which direction it was flowing? When E external was less than the cell potential or the electrical potential or EMF of the cell in this direction. Now, once the external potential is more, the electron is the current is flowing in this direction. And this is the one thing that we this process we use in the charging of the batteries. And this way, so we charge the battery. So when E external is more than 1.1 volt, electrons flow from copper to zinc, and this copper to zinc electrons will flow, because this as soon as the opposite potential is more, means once then more this will become more negative, this will become more positive. So the electrons will move from the negative to positive, means the from copper to zinc, and current will flow from zinc to copper, and zinc is deposited at the zinc electrode and copper is dissolved at the copper electrode. So what will happen? So now the copper, the anode will be oxidizing at this anode. This anode, earlier it was cathode, so that this cathode will become anode, and so here will oxidation will happen because this is behaving as anode. The oxidation will happen, so copper will now dissolve and will go into the solution. It will make copper ions or the cupric ions, and the electrons, the two electrons that are produced will go into this direction, will reach to the zinc plate or zinc electrode, and will now the zinc electrode accepts that electron, and the zinc is now, which whatever has gone into the solution, it will now come in. Those zinc ions will come and combine with the electrons to get deposited on the zinc plate. So this galvanic or voltage cells are consist of. So what we say, this process that one can say is kind of this opposite process is called the electrolytic cell. So if some opposite reaction is happening, so this is what we see in the electrolytic cell. So any further increase in external potential means from here, any further increase in the external potential starts the reaction in the opposite direction. So opposite direction reaction will happen. So earlier zinc was producing zinc 2 plus electron, and copper was depositing. Now the opposite direction reaction will be copper will be converted into copper 2 plus and 2 electrons, and zinc will be deposited at this plate. And now the cell functions as electrolytic cells, and now the cell becomes the electrolytic cells, and this process, this method we use in charging batteries. So why do we charge batteries? Once all the zinc 2 plus ion, whatever the potential is completely to certain level, whatever the depending on the efficiency, if this gets converted to the maximum extent, what we see, we don't see any net difference in this cell. If we see no net difference in the electrode potential of these two cells, no current will be flowing. So once this has saturated, this has come to the maximum level, so what will we do? We need to reverse this process. So we charge this, we connect this to electricity, and electricity, the potential of the electricity is more than the electric potential of this, so that is external potential more than the electric potential of the cell. So what will happen now? The cathode will become anode, anode will become cathode. So now the copper will start going into this, and zinc will now again be deposited here. So once now again after certain time, so whatever the zinc concentration here will be less, and copper ion concentration will be more, and so now cell can again start functioning. Now once you remove the electric plug, and you get this cell ready for the further use. So galvanic or voltaic cells consists of four primary components: a cathode, an anode, an electrolyte solution, and a salt bridge. And what is that? So anode is here, and the cathode. So in this case, in the galvanic shell, the anode is denoted by a negative sign. Since electrons are liberated here, so at anodes, electrons are liberated, and that is why it has been given negative sign, and the cathode is given positive sign. Why? Because it accepts electron, it consumes electrons, so cathode is given positive sign. So anode, at anode, oxidation reaction occurs. So here in this case galvanic cell, and as I said electrolytic cell, both the cells, what happens? Oxidation is happening at electrode. So even if this galvanic cell became electrolytic cell here, when the opposite external potential more than the EMF of the cell. So what we see here again, the oxidation is happening at the anode. This has become anode, and that is why the copper was converted into copper 2 plus and 2 electrons. So the anode always the oxidation is happening, and the cathode reduction occurs in the galvanic cell or any other cell. Anode electrons move out of anode and electrons move into the cathode in galvanic state. So electrons, you have seen electrons move out. So electrons are moving out from the anode and getting into the cathode in a galvanic cell. The opposite. So this is what no the and the cathode and anode together are called electrodes. So we call generally the electrode. So the anode is also an electrode, cathode is also an electrode. So electrolyte solutions provides the medium for the exchange of electrons and ions at the electrodes. The salt bridge that we have seen. So what is the function of the salt bridge? Salt bridge, it's also called the ion bridge. The salt bridge connects the two compartments, oxidation and reduction half cells, as I said, and maintains the electrical neutrality within the internal circuit. And what is that is important? So as I have said earlier, so once this, suppose in an electrochemical cell, galvanic cell, so copper ion is getting deposited here. Nothing is happening to the anion. Sulfate, the copper sulfate is being used. The number of copper ion and sulfate ion are same. And once the copper ions are being used, so what will happen? The negative ion, the sulfate ion concentration will be increasing. It will be more in the electrolyte than the copper ion. So this will become negatively charged. Slowly it will become negative potential will be created here. And because of that negative potential, now the more sulfate ions are there, they will not allow any more copper ion to go and deposit at the electrode, this cathode. Because now the more sulfate ions will be there, they will attract a sulfate ion with copper ion more attractively. So they won't allow after a certain time any copper ion to go and get deposited at the cathode. Similarly, in the case of this compartment, what will happen? The zinc ion is being produced. So zinc ion is being produced. So what we are getting, zinc more and more zinc is being produced, but sulfate ion concentration is still same. So what will happen? So just after certain time, what will happen? So the net positive potential will be created here, and net positive potential, because of that, it won't allow any more zinc ion to come. So it will stop the oxidation of the zinc as well, because the cation that is there in this, if it is more in concentration, so it will stop. It will any more zinc ion to come inside this. So what we do, we use certain device which can provide certain salts if necessary, and don't allow these two electrolyte solutions to get mixed very easily. So in the case of electrolytic cell, the first figure when we saw, what we say, we use these two into the same compartment where we have separated them. Why we have separated them? Because we want the oxidation happen at in one compartment and reduction happen in another compartment. So whatever the electron that has been produced because of the oxidation, that should travel through a circuit, and there we can connect certain devices for our use. This is what we have actually done, and we have planned, and this is what we are doing. But the thing is, once they are separated, and because of this no zinc ion and here no copper ion deposition, no zinc ion production will be happening. So reactions at the anode and cathode by the both places will be stopped after just a certain time. So we need to make these solutions electrically neutral. So we'll add certain salts in these, and this we call the salt bridge. So we add certain things, and this is the jelly, agar jelly is used, and there we add certain salts. The certain salts, the ammonium or potassium cations are there, or the chloride or sulfates are used. So that we will see which ions are used. And what will happen once this copper ion is getting into this, what will it do? It will, the salt bridge will now furnish some cations into this solution, and it will furnish this some cations in the solution, so that this solution remains electrically neutral. At the opposite side, what will happen? Because the plus ions, cations are being produced more and more, so the solution should not become cationic. So what will it do? It will furnish certain anions to make this thing electrically neutral. And so anyway, the cations, the number of electrons that is being produced here and coming here, So electrons are same. So what will based on that it will provide the electrons, and the salt bridge will also be electrically neutral, because based on that electrons how many cations and anions will be going into different compartments, that is being determined. And so everything is electrically neutral, so you can get energy through the cell for a longer period of time, and it will not stop immediately or just after few minutes. So we can get energy for a longer period of time. That is why the salt bridge is added, and salt bridge is added. These solutions are not mixed. Why they are not mixed? Once they are mixed, then this thing is, so we to not let them not mix, we add salt bridge, and also this is the internally it is providing certain ions to make these things neutral. If this was happening in one compartment anyway, the cation and anion will be the same, because here the cation is produced and here the anion is in excess. Though there will be some gradient, the cation is concentration is more here and anion concentration is more here, even in the if they are in the same compartment. So nothing, what is a slight steering would work, and this will be mixed. So anyway, this is what we do. So we use salt bridge or the ion bridge, which connects the two compartments, oxidation and reduction half, and maintains the electrical neutrality within the internal circuit. If there is no salt bridge, the solution in one half cell would accumulate negative charge, and the solution in other half cell would accumulate positive charge. And also what will happen if the positive charge is accumulated here, so positive charge is accumulated in solution, and anyway the electron, whatever the electron has been produced, it has to go somewhere else. And if the more positive charge will be here, so this positive charge will actually not allow this electron to go away. And in the way it is something that this electron will not produce, it will remain with the zinc. And so this is what we see. So if there is salt bridge, the solution in one half would accumulate negative charge, and the solution in the other half cell would accumulate positive charge as the reaction proceeds, quickly preventing further reactions and hence production of electricity. So usually salt bridge consists of U-shaped glass tube filled with the relatively inert electrolyte, and the inert electrolyte, I think these things we will see in our coming class. Next class, I'll start from here.